Navier-Stokes, and we developed the interfacial boundary conditions, which says that there's a jump in normal stress across an interface, which is proportional to the surface tension times the local curvature. Okay. And then we saw that there can also be a jump in tangential stress, which is, so that this simply means a jump, the jump in tangential stress, which is prescribed by the gradient in surface tension. And these can arise if they're gradients in chemistry or temperature within the system. Okay, so that's basically the formal development of interfacial flows, and then it's just a matter of solving problems. So the simplest place to start is to look at statics. So that's what we're going to do today. So this is a meniscus. So this is basically just we have a vertical plate intruding into an interface. I think it's water, air, and you can see that the thing basically goes up and takes this form. So how do we rationalize this? Simplest possible problem. Oh, it's okay, I have handouts here. So you will only have to take relatively minor notes. Okay, so I'm going to do a slightly better treatment of this problem we have here. Okay. Thanks. Okay, so if we go back to this one, let's leave the lights off, but if we look at these equations in the limit, so in a static situation, of course, u is 0, so the stress tensor is simply given by pressure, right? So then the jump in normal stress is just the change in pressure across an interface, okay? And we also see, so n dot I dot S is 0, right? And so this says that if we're in a static situation, because this is 0 and n dot T dot S is 0, then gradient of S has to be equal to 0. So this is again consistent with the conclusion we made last time, which is that you can have no static situation if there's a gradient in surface tension. Okay. Oh, sorry. So our normal stress okay, so this is our okay, so this is if we know how the pressure changes as a function of position, then we can calculate the shape of the interface. Okay, so we'll do that for a few simple cases, in particular the case of the meniscus, where the pressure is going to change owing to the hydrostatic variation. Okay, and the other thing I want to check is that, so tangential stress so this is normal stress boundary condition, tangential stress boundary condition. So if u is 0, then again T takes this form, n dot T dot S is 0. So it tells us that the gradient of the surface tension has to be 0. Which is to say Marangoni stresses imply dynamics. Okay? So let's do this. If we first, our simplest case is a bubble, so we did this just by scaling last time. Okay, let's just imagine there's no gravity. So we have P hat P. Now, so we just want to calculate what okay, so if you look up, so in Bachelor, if we have a vector in spherical coordinates, let's crank this up. Oh. It's manual. Okay. They don't have a fast forward button.
So what are you looking for? Are you trying to
No, I'm just trying to move it up without standing here.
What do you want? More backwards?
Yeah, I'm just going to be using the board for most of today. Yeah, let's kill that one. Very good.
Depois para ligar, é isso mesmo, as besteiras das pessoas.
Okay, so you basically have to look up if you look up the divergence in spherical coordinates, or maybe you have it memorized, you find that it's the following. Okay, so if we're looking at the divergence of the normal, so then the normal is just a unit vector in the radial direction, so this becomes 1, this becomes 0, and this becomes 0. So we have so r hat, so unit vector in the r direction is 2 over r. Okay, so the normal stress so this guy and that's what we got as previously. As typically you, by doing a scaling argument or dimensional analysis, you get everything apart from the coefficient. So here we see that the coefficient is 2, and we can also understand this if you think of there being 2 principal radii of curvature. So these are radii of curvature on surfaces which are orthogonal. Both radii of curvature are r for a sphere, so it's going to be 2 over r is the total curvature. For a cylinder, it's just one radius of curvature is infinite, so it's simply 1 over r. Okay? And this is again rationalizes why the pressure jump is larger for smaller drops or bubbles. Is that a handout? Okay, so now let's look at the static meniscus. So we've seen in the video the surface climbing to match the wall, and basically, so we want to, such a fundamental problem as this, you should understand inside and out, right? So you have to think of it in terms of energies, you have to rationalize the shape in terms of energies, forces, think of it in terms of pressure, all possible approaches. So if we define, so this is a rigid wall, and this is the equilibrium contact angle, theta E, and we're going to call this interface shape nu as a function of x. So x is our direction, our horizontal direction, this is z. And we have gravity acting in this direction. We have density. Let's just imagine this is air water. Okay, so this is, we have a density rho here, and let's just say rho is 0. Think in terms of air, water. Okay, and we know that we have surface tension acting everywhere along the interface. Okay, so what we want is to get nu as a function of x. Okay, so one thing we know is this is basically prescribed by the chemistry of the system, so it can be any number. Right? But given that number, we want to get the shape of the interface. So if that's, notice that if that is less than pi by 2, the water will rise. It's basically saying that the wall is in some sense hydrophilic. It wants to be coated, and then you can also have a situation where it's hydrophobic. In that case, the interface is going to go down like this, right? But in either case, we should be able to solve for the shape of the interface. Okay, so what's so let's write down the force balance. So we basically have to balance pressure jump across here. So if we look at, so what's the pressure here? Atmospheric. Okay, so it's P naught everywhere above the interface, right? And so what's the pressure there? P naught. What's the pressure there?
It's the same,
right? Right. So it's P naught there, and what's the pressure as we go? What's the pressure along here? What? Oh, okay. I say it is hydrostatic, but what is the hydrostatic pressure there? It's atmospheric too, right? Because it's pressure, it's atmospheric there. It's atmospheric here on that as you just cross the boundary because there's no curvature, and then you can step across here, and you're not changing depth, right? So it's still hydrostatic. So it's P naught everywhere along this line. It's when you move from that line that things become things change as a result of the hydrostatic pressure. So is the pressure higher or lower inside? Is it higher there or lower than atmospheric? Right. So we have, so we basically have a suction here, right? And so the pressure here as we move up is going to be P naught minus, so along here it's P naught minus rho g times eta, right? So that's the hydrostatic pressure here. So normal stress balance. So it's P naught minus rho g eta of x equals, so what's the other way that we can get the pressure at that point? Just by going across the interface, right? So by going across the interface, it's going to be P naught plus sigma div of n, right? N being the local normal, okay? Okay, and so n is our, again, of course, it's n at x, okay? So that's our normal stress boundary condition. Let's just okay, so these cancel.
Is that plus or minus the last term?
Plus. We know that the pressure is higher here than here. So does that allow us to figure it out? We can keep track of signs. One always finds out at the end whether things make sense. But okay, we can change them on the fly if you like. We know that the pressure is higher there than here, right? It's lower.
So it should be less than this here.
True. Right. Okay. That means we're going to have to just keep track of signs now. It's all your fault. Okay? Okay. So in any case, so this is our force balance then. So this is the so-called Young-Laplace equation, where you have a balance between hydrostatic pressure and God, I've changed signs here all the time. Okay, okay. Here we go. You'll notice that the sign is changed on my notes too. It changes every single time I do this.
So the left side is pressure inside the fluid in the meniscus, and the right side is outside, right? Where you change the plus and minus sign.
Yeah, just inside. Yeah, just as you come across the interface.
It's two ways of calculating this compression, the same point.
Right, so it's actually just on this side of the interface, right? This is the way the argument goes. So you basically go, we can get there by doing that, or we can get there just by crossing the interface here.
Oh, okay.
But you'll notice that even on these notes, there's a hand sign change. It changes every time I do it, but we always get the right answer. That's the good thing about signs when you're doing physics. They have to make sense. Okay, so right. Now we have to figure out how to compute this. So I discussed this a little bit in the appendix of the notes. But so notice that the shape is generally going to depend on the density, the surface tension, and the equilibrium contact angle. Okay, so let's compute the normal. Okay, surface. The surface is defined z of nu of x, so we can define a functional that vanishes on the surface. Okay, so if this vanishes on the surface, then we know the normal So if you remember your first class in vector calculus, you'll remember this. So this is then this is just the normal to a two-dimensional curve. So we're gonna have sign errors in every single equation. So I won't worry about it. Okay, so but now, oh no, so we don't want to do that. So if we linearize, we can do that, but we don't have to linearize. Okay, so we can then calculate this is the divergence. So the curvature now, and we have see this in the appendix, div of n minus mu xx over 1 plus mu x squared. Oh wait, sorry, this is wrong. This should be 1/2 here. Sorry, I mixed two steps. This is 1/2 here, and this is 3/2. Okay, so in your notes, I just linearize it and solve this equation with the linearized div of n, which is valid provided this angle is small. But you can do it in all generality. Okay, so if we substitute this in here, this should be new because this is a right. This is a. Sorry, Dre.
So what exactly mean linearize? I know for small angle, but
yeah. So you say basically small.
Non-linear.
Yeah, so exactly. So you linearize and imagine nu x itself is small relative to 1. So when you square it, you basically throw this term out.
Oh, so you're going to throw that out?
Yeah, no, I'm not actually, but that's what I do in my notes. So I do a simpler solution in the notes. I'll do it completely here.
Okay.
Okay?
Oh, gotcha.
Right. Okay, so here we have then minus, oh God, okay, rho g nu equals sigma div n equals sigma minus mu x 1 plus mu x squared to the 3/2. Okay? Okay, so in notes, okay, so how do we solve this exactly? How do you make this differentiable? You guys are math students. What do we want to multiply both sides by? To make both sides differentiable.
Understand your question.
What's that?
I understand the question. You said
How do we make these?
Duration factor kind
Kind of. If I multiply both sides by one term, then we can integrate both sides directly. Because otherwise it's not clear how to do this, right? But we can get one integral directly. Time's up. All right. Okay, so then both sides become exact differentials. So we can get the first integral. Okay, we're good with that? I'm going to leave you guys. Actually, so as you get older and as a professor and you get lazier and more technically inept, you have to ask the students to cut you slack. So I used to say, okay, you guys are responsible for sign errors. So now you're responsible for sign errors, and I'm getting even older, so it's sign errors and factors of 2, right? So I'm not responsible. You guys are responsible for finding sign errors and factors of 2. So that'll make my life easier. Okay, so here we have the equation. So, and notice that we can, so d by dx of nu squared over 2 equals, we can introduce our capillary length now. Okay, so this basically has all the material properties in it apart from the contact angle. Okay, so integrate from x to infinity. So the left-hand side so what's nu at infinity? Nu at infinity is 0. Okay, on the right-hand side, okay, so again, so we just do the integral and we evaluate this at infinity. The slope is going to 0. So nu x squared 1/2, and this is 1 minus sine of theta. Okay. So theta is this angle here. So then theta becomes theta E at the contact line. Okay? But theta is a function of x. Okay, so we have then sigma sine theta. So this is a pointwise statement along the interface plus 1/2 rho g nu squared is equal to sigma. So that gives us the shape of the interface, and we can at the maximum deformation, at the maximum height, so yeah, nu equals h, so h is our maximum deformation here. We know that theta is equal to the equilibrium angle, equilibrium contact angle. So the maximum rise height so this is sort of consistent with our intuition that the capillary effects are important over a length scale, so you expect, so basically surface tension is the only reason this thing is deflecting from the horizontal. Gravity wants to keep everything flat, but there's a small region in which surface tension is important, and that is on the scale of a capillary length, as we see here. So it's on that scale. But the details of the geometry depend on the chemistry. So in particular, the sign of the equilibrium contact angle. Okay, so other ways to think about this and to drive these equations, as I say, it's such a canonical problem, you should try and understand from every different perspective. Okay, so if this is if we imagine, say, this green chunk here, so what are the total forces acting on that body? So actually, let's make it purple. Okay, so think about what forces are acting on this guy. So horizontal forces. What horizontal forces are acting? On this guy. Is pressure where? Right? And is it high or low? Right. So it's going like this, right? Right? Space is increasing linearly. So you have suction in that direction. Right? You have surface tension pulling. Right? So it's in the horizontal direction there. And in the tangential direction here. Okay? So anything else? But let's look at horizontal first. Okay? So those are all the horizontal forces acting, right? There's nothing acting here. So just to say the atmospheric pressure is 0. So, so the horizontal force balance then is sigma sine theta. So that's this tension pulling in that direction.
Is the pressure going up the triangular pressure distribution instead of?
So it's 0 here and going up. It's suction. So the hydrostatic pressure gets lower and lower as you go up here. So the suction gets higher and higher.
So
Yeah.
the graph is minus pressure.
Yeah. Okay. We're basically getting suction in this direction, and there's more suction up here than down here. Yeah. Okay, so this is so we can get the net contribution there just by integrating rho gz from 0 to nu, right? So you do that and you get 1/2 rho g nu squared. And then we have sigma pulling to the right. So these are both pulling to the left. Hydrostatic suction. And this is again the horizontal component of this surface tension force, and this is just pulling. Maybe I should call these something. I can call this T. And this is T2. Okay? So notice that is exactly equal to this equation here. Okay? Yeah. As long as it's not a sign question. Yeah, go ahead.
So what you get is actually the differential equation for the surface, for the curve.
Yeah.
And it's not as simple because it involves sine of the first derivative.
Yeah.
Well,
Yeah, so we'll in practice, once you've got the end condition, then you can integrate it, right? So, but you need to know the end point, right? So this is the end point because we know everything in there, and then you can just shoot, right? So you basically have this and the slope.
yeah, well,
Right.
numerically you can estimate it, but if
Yeah.
you have an analytic expression, can you get it for the same?
Yeah. Yes. So you can. I did it for the linear case, and then this is the nonlinear case. So let me just continue here, and we'll see what we get at the end. Okay, so this is again the same as this equation. Okay, so if we look at the vertical force, so what's contributing to the vertical force? Acting again on this chunk. So this guy's not contributing at all. What is contributing?
The tangential pressure,
And what's that balancing?
the weight.
Right. Right. So the weight we get by integrating from x. So this is again x here, from x to infinity, rho gz dx. Okay. Okay, so if we set x equals 0, then we're getting the whole weight of the meniscus. If we set equal to 0, where so sigma cos theta E is equal to the total weight of the meniscus okay be displaced in meniscus. Okay, so we can see then immediately that the sign changes with theta E. So if theta E so according to whether the surface is hydrophilic or hydrophobic, so if the surface is hydrophobic, then it will repel the water. And you'll get a situation like this. Sorry. So okay, so this is a hydrophobic but you see the general features in the absence of surface tension. When we simply have a flat interface, but there's this small region in which surface tension dominates. So in particular, the contact angle, which is determined by all three of the surface energies, prescribe this angle, and then you have to match onto the far field. Okay? And this happens basically over a length scale, which is of order L capillary. Okay? Now where were we? From this, you can write down the shape. You can integrate this, right? To you have nu as a. This gives you. Yeah, I might have to show. I guess you have to do it numerically, right? In the linear case, you have a simple expression, right? It's basically just dies exponentially. And that's what I have in the notes here. I'm just trying to think you'd have to do it because you know initially what this is and this is, and so then you can go, right?
Yeah.
So you know what the slope is. So you basically just shoot to the.
Yeah, I know.
Yeah. Okay, so we want to now. Any questions? How are we doing there for time? All right. So we want to now generalize Archimedes' principle. So Archimedes was an incredible guy. If you want to read something mind-blowing, read his treatise on floating bodies. So he looked at objects floating at interfaces, and he basically, without knowing calculus, calculated the stable configurations of these bodies. So, for example, if you have a cylinder and it floats and it has some density which is intermediate between that of the fluid and that of the overlying air, then it will align itself so that its corners are sitting on the surface. Try doing that without calculus. So what we're going to do now, and we all know Archimedes' principle, and we're going to generalize it now to the case where objects are small. So when objects are small, interfacial forces can also play a role in flotations. Okay? So Archimedes' principle is basically that the force acting on a body in a fluid is equal to the weight of the fluid displaced. And this is true both at within the bulk of the fluid and if you have a floating body, so a body at an interface. But the question is, how does it generalize to the case where the object is small so that surface tension comes into play? Okay, so generally, okay, so we think basically you have some object sitting at a surface is going to sink or swim according to how dense it is relative to the ambient. That's our general intuition. So like things, I mean, rho of the particle is less than rho. Let's just say rho is equal to 0 here. Okay, so when we've seen previously that if this thing distorts the interface, so the interface looks like that, and there's going to be some vertical component of the force balance which can contribute to weight support. Okay, okay, so so how do we calculate the force acting on some body floating within a fluid? So let's imagine it has density rho sub p, and we know that the pressure is increasing linearly with depth. At an amount prescribed by the density of the fluid. Okay, so we know basically that because of this hydrostatic gradient, the pressure is higher here than here, so there's going to be a net force which bears its weight. And the question is, when is that force large enough to support its weight? So let's compute. This can be any shape. I've drawn a sphere, but it can be anything. Okay, so the hydrostatic force we've seen that in general the hydrostatic force or the hydrodynamic force acting on a body can be deduced by integrating the the normal component of the stress tensor over the surface of the body. Okay, so this is this is the surface of interest. Here's the surface of the body. And in general, the stress tensor looks like this. And if we're in a static situation, we get rid of this. Okay, so for this particular case, so the hydrostatic force acting on this floating body nice. Yeah, so I'm Skyping me. I guess I better log out. Okay. Sorry. Okay, so Pn ds. P is just now. So minus rho gz n ds. Right, so we're basically integrating the pressure everywhere around here, and it's varying because of the depth of the surface varies. And we can use divergence theorem to turn it into a volume integral. So it's minus rho g, then we have the integral. So grad of z is something in the z direction, so it's minus rho g okay, so that then is precisely equal to the weight of the displaced fluid. Okay, so that's the force which we've gotten by integrating the hydrostatic pressure over the surface of this body. Notice that it can be any shape you like. All that comes out is the volume of the body. Okay, so we see then that we expect the object. We now know the hydrostatic force which will act on the body. So the question is the magnitude of that relative to the weight of the object. And this will determine whether it sinks or floats. So Archimedes' principle. So in this force, the weight of the body is rho particle gv. So the thing can float if the object is less dense than the fluid. Otherwise, it sinks. Okay, let's have a little break. 5-minute coffee break.